We're going to look up chapter 4, and we're going to start in 4.1. Chapter 4 is all about exponential and logarithmic equations and graphs and functions. And so we're going to start off by graphing and kind of relating things to what we already know graphing wise. So here's your bell work. Go ahead and pause this here, and you can attempt this bell work here. All right, now that you have attempted the bell work, both of these are parent functions, and these are exponential functions. And I know that these are exponential functions because x is in the exponent. Okay, so we're going to have several different types of parent functions. And as we've said before several times, if you do not know how to graph something, or if you don't know what the graph of something looks like, you need to make a table of values. Okay, with exponential graphs, we want positive and negative numbers and 0. Okay, so this 2 to the x here will be in blue. So I like to pick the same numbers. So -2, -1, 0, 1, and 2. And when I plug those in, so I have 2 to the -2 and 2 to the -2. Remember that negative in the exponent makes it a fraction. So we have 1/4. 2 to the -1 is 1/2. 2 to the 0 is 1. Anything to the 0 power is 1. And 2 to the first is 2. And 2 squared is 4. We'll go ahead and set this table up for y equals 5 to the x. We're going to use the same values. And these are the values I always use for parent functions, exponential parent functions. You could use other ones. It doesn't matter. I tend to use these for all parent functions. It gives me a range of positive numbers, negative numbers, and it keeps them rather small. So we have 5 to the -2, which would be 1 over 25. Whoop, I need that in red. 1 over 25. 5 to the -1 is 1 over 5. And 5 to the 0 is 1. 5 to the first is 5. And 5 squared is 25. And you'll notice a pattern here on all these that it's kind of the reciprocal. Okay, these negatives are the reciprocal of these, likewise here and here. And that's true for all parent functions, that you'll have those reciprocals. Okay, so if we start our graph here, and I'm going to definitely run out of numbers here because that one goes all the way to 25. But we can kind of get an idea of where our graph is. Okay, so we have -2 1/4, -1 1/2, 0, 1, 1, 2, and 2, 4. So this blue one's looking like that, and it'll just keep growing. And then the red one, so we have 1 over 25, so it's actually less than that one. A fifth, so less than that one. 0, 1, 1, 5, so way up here. And then this is 125, so it's not even anywhere close to this graph. So this one's going to come here, kind of be below this graph, and then intersect at 1, and then cross back up. So it'll be below here, but then grow much quicker on the positive side. So looking at this, these are both exponential growth. We have exponential growth and exponential decay. Both of these are growth. Okay, they cross at 0, 1, and they just, they climb at different rates. We do have horizontal asymptotes here. Both of these, all parent functions, start with the y equals 0 horizontal asymptote. And we can shift these up, down, left, right, and kind of do all sorts of things with them. And that's what we're going to look at in chapter 4. So 4.1 is exponential functions. Our goal here is to apply properties of transformations to the exponential parent functions. So we are still going to look at HBAK, domain and range, still all looking at this. We are not going to look at B. And I just want to address that real quick, that the reason why we don't look at B. And the reason being is because these are exponents. You can represent the same thing with just a different base value. That is, if we look at 8 to the x, that is the exact same thing as saying 2 to the 3x. Okay, yes, 3 would be a horizontal compress, but 2 to the third is 8. So we don't need to worry about this b value. That's the same thing as if I say like 1/4 to the x. That's the same thing as saying 2 to the -2x. So I could flip this over the y-axis and compress it by 2, but instead of doing that, I'm just going to look at this parent function and do it that way. Okay. So we're not going to be dealing with b in this sense. Our b is right here. These are the b values that we're going to look at for exponential. So we have the HAKDR moving things up, down, left, and right, and stretch and shrink and compress. So exponential function with a base a, anything with x as an exponent is exponential. Okay, we've kind of worked with this formula a little bit before. Notice b would be right here, but now this is kind of our base of the exponent is our new b. So just a reminder here, h, the opposite of h goes left and right. So positive will go left and a negative will go right. A out front is a vertical stretch or compress. A number bigger than 1 will stretch it, and a number between 0 and 1 will compress it, and a negative will flip it over the x-axis. For k goes up and down, so positive up, negative down. Okay, and that's all we're doing here with these. This b here, however, is your parent function. It will tell you, do I have exponential growth? Or do I have exponential decay? And we will look at what kind of numbers give me the growth versus decay. So let's look at just general evaluating here. So here I have f of 5. So we're going to plug 5 into the f function. And a lot of times you can use a calculator for this, but we want to make sure that we see some kind of work here. So I want to see what you're plugging in. Sometimes it may ask for an exact solution. Okay, so if asked for exact, you don't want to do any rounding or put it into the calculator. So here I have 3 to the 5th, and 3 to the 5th is 243. In this case, I have 3 to the -2/3. Now, on this one, let's say they ask for the exact solution. Okay, well, negative exponent makes it a fraction. So we have 1/3 to the 2/3. I can turn this fraction into a radical. So that would be the third root of 3 squared under 1. Now I can't have a radical on the bottom. I need a group of 3. I already have 2 of them. So we're going to multiply the top and bottom by the third root of 3 to kind of cancel that on bottom. So I have the third root of 3 over 3. which is about, if I put that in, about 4.481. So 0.481. And these little squiggly equal lines just means that I rounded somewhere. Between here and here, I rounded. Okay, so pay attention to what it's actually asking for. Is it asking for an exact solution, or is it telling you to round? Now, problems like this with a really weird irrational number, we're going to round those. So this would be 3 to the pi, and 3 to the pi is nope. 1.54. And then here we have 3 to the radical 2. We could kind of play with this one a little bit, but we'll just put this one in the calculator. So 3 to the radical 2 is 6.705. Okay, so be ready to work with those exponential numbers. Okay, draw the graph of each function. Now here you can see that these both are parent functions, but they're reciprocals of each other. I have 3 and then I have 1 over 3. So if we make a table here, we're going to say x, f of x, and then g of x. So we're going to use the same x values. So we're going to have -2, -1, 0, 1, and 2. I'll do f of x in blue here. So 3 to the -2 would be 1/9. Okay, again, the negative makes it a fraction, and then you have 3 squared is 9. 3 to the -1 is 1/3. 3 to the 0 is 1. 3 to the first is 3, and 3 squared is 9. Now here, okay, we've got 1/3 to the -2. So we're going to flip this over with that negative and then take it squared. So this one is actually 9. 1/3 to the -1 would be 3. 1/3 to the 0 is 0. 1/3 to the first is 1/3. And then 1/3 squared is 1/9. So you can see here that these just like flip-flopped. Okay, the 1/9 here came down here. The 3 switch spots. Oop, this should be a 1, not a 0. Okay, so if we graph these, start with blue here. So we're at -2 1/9, -2 1/3, 0 1, 1 3, 2 9. Okay, so here's this one. It's kind of growing like this. Okay, again, I still have this horizontal asymptote at y equals 0. And then this one, we're at -2 9, -1 3, 0 1, 1/3 here, and then 1/9. So we have this right here. Whoop, I was supposed to go through that point. Okay, so notice here, I still have y equals 0 as my horizontal asymptote. Notice here, I had a number bigger than 1 versus a number between 1 and 0. Just like the vertical stretch and shrink with B as before, or even with A, those numbers do things. Okay, so this is a growth. Okay, this red one was a decay, and this blue one was a growth based on that number. So growth will be a b value greater than 1. Decay will be a b value between 0 and 1. Okay, so those numbers are going to dictate which way your graph goes. Now, if we think about it, these are really the same graph. I just flipped it over the y-axis. Well, if I take 3, or let's take this 1/3. 1/3 is 3 to the negative 1 x, or to the negative x. That's telling me I'm taking this 3 to the x parent function and flipping it over the y-axis, which is exactly what I did to get that red graph. Okay, so instead of dealing with a negative b, I can just deal with a fraction here, and it accomplishes the exact same thing. Okay, so you have exponential growth and exponential decay. Okay, here we're going to actually find the parent function equation. So here's my equation that I want. Okay, so I'm saying f of x equals what number to the x power? Well, in this case, they give us this point right here. They actually give us 0, 1, but that's not really going to benefit us any, because anything to the 0 power is 1. But they give me the point 225. So what they're saying here is they're saying 2 to some power, or sorry, they're saying some number squared is giving you 25. Well, what number squared is 25? That number would be 5, and that gets you your parent function there. Over here, they're saying f of x equals some number to the x. Okay, same question. They give you the point 318. So here they're saying what number to the third power equals 1/8. Okay, so what number times itself 3 times is 1/8, and that would be 1/2. So we can kind of play around with some of those, and we can do the evolution of kind of exponential and how you can go through a line and get them more curved than others, depending on what b value. B, how does 2 to the x versus 10 to the x versus 1/10 to the x, how do all of those compare? And that's kind of what we would do in the evolution of exponential. Okay, so let's look at our next problems here, which is kind of the meat and potatoes of what we want to talk about. So we're going to do all these on one graph. And we're going to look at graphing them, but then stating domain, range, and the asymptote. So all of these have 2 to the x parent function. So we're going to start with graphing that. And I want to see your parent function table, or at least your parent function on the graph here. So -2, -1, 0, 1, and 2. So that's 1/4, 1/2, 1, 2, and 4. And as you keep doing this, these are going to be easy. Like, you're going to have them memorized just like an x squared or x to the third. So -2/4, -1/2, 0, 1, 1, 2, 2, 4. Okay, this is your parent function. All parent function asymptotes start right here at y equals 0. Okay, so that's where your asymptote starts, and I can stretch, shrink, flip, shift. I can do all of that with the asymptote, just like my graph. And these are only dotted because it's not my ending graph. So this first one we'll do in blue. It's kind of written a little bit backwards than what we normally see. So 2 to the x plus 1 is the same thing. Okay, so this is the parent function, and that plus 1 has it go up 1. So in this case, all I'm doing is I'm taking these 5 dots and I'm going up 1. So this would go to 1. This would go from 2 to 3. This would go 4 to 5. This would go half to 1 1/2, a fourth to 1 1/4. And even your asymptote would get shifted up 1 spot. So now your asymptote is y equals 1. And your graph is going to look something like that. Okay. So if we look at domain would be all reals. And your range, the lowest number I can have is 1, but I really can't even have that. So parenthesis 1, comma, to positive infinity, it's going up. Okay, here on the next one, I just have this negative out front, and that's a negative a, and a negative a flips it over the x-axis. Okay, and then we'll look at domain and range. So we have to go back to the black graph here. So this is 1/4. If I flip it over, it's going to go negative 1/4. So negative 1/4 maybe here. This would go negative 1/2. This would go negative 1, negative 2, and negative 4. So we're looking here. And my asymptote here is on y equals 0. If I flip that over the x-axis, it actually stays on the x-axis. Okay, so your asymptote for this one is also y equals 0. Domain is all reals. And your range is negative infinity, because the arrow goes down, negative infinity to 0, but you can't have 0. So both of those get parentheses on it. Okay, and here on this one, we'll do in green. So this is an H inside. So the opposite of that goes left and right. So this is going to go right 1. Domain, range. Okay, so if I take the black ones and go right 1, so from here to here, here to here, to here, to here, to here. Okay, so we're just shifted everything to the right 1 spot. Okay, and if I shift my asymptote to the right 1 spot, it stays right there at y equals 0. So your domain didn't change any, all reals. Your range, I didn't move it up, down any, so your range doesn't change. So it's 0 to positive infinity. Lowest number I can have is 0. I can't actually have it, which is why it gets parentheses, and then it goes up forever. Okay, so let's try something a little bit more challenging here with this concept. Okay, let's take the equation y equals, I don't know, 2 to the 1/3 x plus 1. Let's do a negative here, minus, well, let's do plus 3. Okay, so if we look at our parent function is 1/3 to the x. So that's going to be exponential decay here of a growth of, or a decay value of 3 or 1/3. So h is going to go left 1. No b, a is going to go over the x and vertical stretch by 2. And then our k is going to go up 3. So if we, and we'll do domain and range here in just a second. So if we graph our parent function first, okay, so that's -2. So our parent function here, if we do a table, -2, -1, 0, 1, 2. So 1/3 to the -2 is 9. to 1/3 to the negative 1 is 3, 1, and then 1/3, 1/9. So I'm at negative 2, 9. So here, and then negative 1, 3, 0, 1, and then a third and a ninth. Some of those fractions are kind of hard to get placed right on your graph. Ooh. Okay, so something like that. Okay, so then we need to follow this order. So I got the parent function. Now I'm going to go left 1. Okay, let's start here with the fraction. So I go left 1. I flip it over the x-axis. So here, flip it over. Now it's at negative 1/9. And then I vertically stretch it by 2. So that's negative 2 over 9. So it goes just a little bit more. And then up 3. So 1, 2, 3. Okay, here we're going to go left 1. We're going to multiply it by, or flip it over, then multiply it by 2. So we were at negative third. Now we're at negative 2/3. And then we are going to go up 3. So 1, 2, 3. Okay, 1, there's 0, 1. So we go left 1, flip it over, multiply it by 2. So we're at negative 2, go up 3. 1, 2, 3. Okay, here we're going to go left 1, flip it over. So that's negative 3. Multiply it by 2. That's negative 6. Go up 3. That's negative 3. So if I do this last one, it's not even going to be on here. So here is kind of my graph right now. We also need to do the asymptote. So the asymptote starts here at 0, y equals 0. If I move it left 1, you don't really see that. If I flip it over the x-axis, it stays right there. Vertically stretch it by 2, well, multiplying 0 by 2, you still get 0. And then if I move it up 3, it goes to plus 3. So y equals 3. And then your curve kind of goes along with that line. Okay, domain-wise, we're at all reals. And which is true for all exponential. And then range-wise, we're at negative infinity because we flipped it over, and it goes up to 3. And I can't have 3, so I get a parenthesis there. Okay, these are the kind of problems that we want you to be able to do. Okay, we're going to skip this because it's just changing the window and kind of seeing how they compare. So we're going to skip this problem and get into compound interest. Compound interest is the greatest thing, one of the greatest things in the world that was created, and it really helps you gain interest on accounts, and it's also just a really easy way to calculate loans and savings accounts and things like that, used in the banking industry a lot. Okay, so the P here stands for principal. And the principal is the starting amount of the account. So you have $1,000 to start with. To put it in an account, it's $1,000. R is your rate, your interest rate in years or per year. T is time in years. N is the number of compounds per year. And we'll talk about that here on the next slide. And then A of T, I should have done that first. A of T is the amount after or at time t. Okay, so however much is in the account after 5.5 years or whatever it is. Okay, so you're going to use this. You're going to need to know this formula. I'm not giving you this formula. You need to know it. Okay, a sum of $1,000 is invested at an interest rate of 12% per year. Find the amounts in the account after 3 years if interest is compounded annually, semi-annually, quarterly, monthly, and daily. So we're going to look at all 5 of those. Okay, so if something is compounded annually, that is one compound per year. So your N is 1. Semi-annually happens twice. So you're going to compound in like month 1 and month 6, or just 6 months apart. It doesn't matter really when it happens. So N is going to be 2. Quarterly would be 4 times a year, so N is 4. Monthly, there are 12 months in a year, so that'd be 12. And daily would be 365 unless it's a leap year. And here in this case, banks often use for daily, because if you get out a loan from a bank, it's going to be compounded daily, especially student loans. But a savings account is only compounded quarterly. So that allows the bank to get more money than paying to borrow our money. But anyway, banks usually use 365.25. This way they don't have to recalculate the formula every single year or every single leap year. Every 4 years, they can use the same formula every year. Okay, so to fill this out for each one, so we're going to have 1,000 times 1 plus R, which is 0.12. It's 12%, but that's 0.12 over 1. And then T, which is 3 times 1. Okay, there's one of them. And then we're going to have the same thing, except instead of 1 here and here, for N, I'm going to put a 2. So it's 1,000, 1 plus 0.12 over 2, 3 times 2. And then 4, so 1,000, 1 plus 0.12 over 4, 4 times 3. We have 1,000, 1 plus 0.12 over 12, 3 times 12. And then our last one would be 365. So 1,000, 1 plus 0.12 over 365. 365 times 3. Okay, be careful, please, putting these into the calculator. When I put these into the calculator, I get $1,404.93. For semi-annually, I get $1,418.52. For quarterly here, I get $1,425.76. For monthly, which can happen as well, credit cards are done often monthly, but they can also be done daily as well. So let's see, I get $1,430.77. And for this daily one, I get $1,433.24. So as you can see, the difference in once a year and daily is only about $30. Okay. Now, to us right now, $30, or to you as a student, $30 is pretty good. Like, that's a good amount of money. But in the overall scheme of things, $1,000 versus $30 is not really that much compared to $1,000. Now, I will take an extra $30. I'm going to go pass it up, but you're still not gaining a whole awful lot. Okay, especially after like after monthly. Okay, when you go from quarterly, monthly, that's a $5, and then monthly to daily, that's only $3. That's not a lot. Okay, so somewhere monthly or quarterly is going to be your kind of sweet spot there that you're actually going to be able to find. Okay, last problem here. Find the annual percentage yield for an investment that earns interest at an interest rate of 6% per year compounded daily. Okay, so our percent yield here, we're still going to use this formula. Okay, so we have A equals principal 1 plus R over N in T. So we have 6% compounded daily. So N is 3. So we have A equals P 1 plus 0.06 over 365. 365. And we're going to look at 1 year because it's annual. So we're looking at 1 year there. So if I calculate all of this part right here, this portion can all be done in the calculator. So I get A equals P to the 1.06183. Okay. If we look at the simple interest formula that we kind of did a while back, it's A equals P with the 1 plus rate. So this is 1 plus 0.06183. And this number right here is your annual percentage yield. Okay, so which would be 6.183%. Okay, so that is your yield for 1 year. Okay, if you had 5 years, it would be different. Okay, so this part right here is kind of old stuff. We had the 1 plus and the 1 minus problem or formula that we were using. Okay, so that's 4.1. We're going to kind of continue this not the exact same thing, but we're going to still be doing some exponential graphing in 4.2. And then as we move forward, we're going to get into solving and doing some other stuff with it. If you got questions, feel free to reach out. You do have an assignment on WebAssign.